Hi everyone, and this is the first video on a series that I'll be doing about fun problems in group theory. And these problems were chosen from various sources, which I'll link in the description. In this case from Tim Gowers' website, which was run a couple of years ago and it shut down, I think, but there's a lot of great articles still up. And they're selected so that they show illustrative examples of certain techniques that are useful in group theory and more generally algebra, and they show important ideas that are good to keep in mind in a more general context. So this is fun group theory problem number 1, and it goes as follows. We're going to let G be an arbitrary group as long as it has a subgroup H of index n. So index n being you have n cosets of H in G. Show that G has some normal subgroup which has an index dividing n factorial. So at first, it might seem like we don't have a lot of information, and that's true. We only have some subgroup of index n, and suddenly we're supposed to conjure up some kind of normal subgroup which has index dividing n factorial, which is a different number. But we're going to exploit some relationships here between this n and n factorial, the idea of having indices, we're going to use the isomorphism theorem, and the fact that we have normal subgroup that we need to pull out. So idea number 1, we want to think of this normal subgroup in a certain way. And even though the definition of a normal subgroup is one that's closed under conjugation, right? If you have H normal, then GHG inverse for any group element G is equal to H at the level of subgroups. But in practice, we want to think of normal subgroups as kernels of homomorphisms. So we want to think of normal as kernel of some homomorphism. Okay, and one can check that there's actually a correspondence between kernels of morphisms and normal subgroups. Right? If we start with a normal subgroup, then it's the kernel of the morphism that's just the projection from the group to G mod H. And conversely, if you have any group homomorphism, it's a trivial exercise in group theory to check that the kernel of this morphism has to be normal. It's closed under conjugation in the domain group. Okay, so in this case, we want to find a normal subgroup of G that has index dividing n factorial. So n factorial is much bigger, which means we want to find a homomorphism with a large kernel, right? So we want to furnish a morphism from G to something else such that we have a kernel that is going to be this normal subgroup, which we want to have index dividing n factorial. So how do we do this? Well, we also want to think of group actions, and this is really the crux of this video, to highlight why group actions can be used to prove even somewhat, I guess, mundane or routine problems in group theory. So in this case, we want to think of, let's say, action G on a set X is the same as a morphism G into what I call sigma of X, i.e. the permutation group of X. So this consists of all permutations, and this in some sense, if X is a finite group, say, is isomorphic to the symmetric group on n letters. So we want to ultimately furnish some kind of set such that we have a group action into the permutations on X, and eventually we want that kernel of this morphism or this action to correspond to the normal subgroup as desired with index dividing n factorial. So let's think about what properties we want X to have and how we can furnish it just given the subgroup H of index n. Okay, so we would like the kernel of the morphism from G to the permutations on X let's call it K, to satisfy the index of K in G to divide n factorial, right? So now, with this in mind, this is the same. Let me do if and only if, because we know that the index of a subgroup in G is the same as the order of G divided by the order of K. This divides n factorial. And this, of course, happens if the order of, let me put this in parentheses, the quotient group G mod K has order that divides n factorial, right? You just divide the orders of the group by the normal subgroup. Okay, so now how do we ensure that the order of this quotient group divides n factorial? Well, let's take a subgroup of size, let's take a set if X has cardinality n, then we have sigma of X let's say cardinality of sigma of X equals n factorial, right? Because if we have a cardinality n set, then we have n factorial permutations on it. Okay? But why is this important? Because the first isomorphism theorem, right, is that G mod K is that this is isomorphic to the image of this morphism, which I'll call phi. I know I didn't call it phi earlier, but I'll call this phi now. So because of this, right, the image of phi is going to have it'll be a subgroup of this permutation group. So by Lagrange's theorem on sizes of subgroups, its cardinality, which is actually equal to that of G mod K, divides n factorial. That is, it divides that of sigma of X. So this is how we are going to proceed. And we are now going to furnish the set X. Right, so how do we make this set X of cardinality n? Well, where does this n originally come from in our problem? Let's remember that this is because we have a subgroup of index n. So we have this to be true, and by definition, so H has n cosets in G. Okay, so we can take a cardinality n set to be the cosets of H. Now, one small thing arises, and that's the fact that H is not necessarily normal, so its left and right cosets need not coincide. Let's make a choice here, which turns out to be the right one, well, the correct one, I should say. We're going to pick the left cosets, which is usually standard. Take the sets of left cosets of H in G. And this is going to have cardinality n. Call it x. So now we know that cardinality x is n. Now, to essentially finish this proof, we have to take an action from G to the left cosets of H. So make G act on the left cosets of H. Let's choose, or basically try out in this case, choose the action that is going to take for, let's say, group element G and a left coset XH, so we're left multiplying by X. G as it acts on XH is just going to be GX times H, or I'll just write GXH. So let's check that this is an action. Right, so we will define actually this map above, which took XH to GXH, the map phi sub G. And now we need to check that when we compose phi G and phi G prime, we get phi G times G prime. So now, say that we have two different elements, G and G prime. Let's take phi of G prime XH equals phi of G. Now this is going to act first, so we have G prime XH, and then G is going to act, so we have G times G prime XH, and this equals phi G prime XH as desired. Okay, so this proves that this is a valid action, and now our problem is solved, right? Because we have chosen an action G on X, right? And the kernel of G, when we regard it as a morphism into the permutations of the left coset space, will give a subgroup K such that the index of K in G divides n factorial. And this concludes our proof. So hopefully this shows why group actions are important, and this sort of idea is ubiquitous in group theory. You can use group actions, and I'll probably follow this up by showing results about groups of cyclic groups, Cauchy's theorem, which predated the Sylow theorems. Sylow theorems are extremely important, and basically all of them are chosen or proven through some kind of judiciously chosen group action. You can look at more results about groups acting on sets or spaces, groups of certain order, like prime powers of order p times q, where p and q are primes. And so I'll follow this video up with some others, hopefully in the same vein. Thank you for watching.